Classical binary logic operates on a strict, unyielding dichotomy. Every variable must be either true or false, 0 or 1. But real-world reasoning rarely offers that level of clarity. We constantly encounter missing context, incomplete information, and profound ambiguity. Forcing an ambiguous real-world variable into a strict binary framework inevitably breaks the system. It forces logic gates to compute arbitrary guesses instead of actual facts, producing cascading errors. To process reality accurately, we have to expand our basic mathematical architecture. We need a distinct third value dedicated entirely to the unknown. This is the bottom state, written mathematically with this symbol. It does not represent a number greater than 0 or 1. It represents the state of absolute minimal information. A functional logical system cannot simply demand certainty where none exists. It has to learn how to mathematically encode ambiguity. Processing 0, 1, and the bottom state requires a completely new piece of hardware, a ternary logic gate built specifically for this three-value environment. We call this theoretical architecture the Trigate. Like a standard logic gate, it accepts two primary data inputs, which we will label A and B. But it also requires a special third input, labeled M. In classical engineering terms, we would initially interpret M as the logical mode. The question is how this specific arrangement allows a circuit to process a completely unknown variable without collapsing the calculation into an error. Decoding the internal mechanics of this single gate gives us the blueprint for building systems that can compute with unknowns without falling into binary error. This table maps the Trigate's behavior based on standard engineering assumptions. Columns for inputs A, B, and M determine the output. The rows break down into three distinct blocks based on M. When we set M to 0, it behaves as a ternary AND gate. Switch M to 1 and it functions as a ternary OR gate. When M drops into the unknown bottom state, the gate only produces a defined output if inputs A and B perfectly match. The obvious conclusion is that M acts as a multiplexer. It looks like an external switch toggling the gate between three entirely separate operations. Treating the Trigate as a multi-mode switch is an illusion. It masks a much simpler mathematical axiom operating underneath. The mode input does not select the operation. The entire truth table is actually governed by a single, unified rule. The Trigate is a single ternary majority function. M is a third co-equal vote on the scale. If any two inputs vote for 0, the final output is definitively 0. The unknown bottom state does not derail the calculation. But if inputs are 0, 1, and an unknown bottom state, there is no clear majority. The scale remains balanced, mathematically forcing the output into the bottom state. The system actively refuses to consolidate a defined interpretation without a clear mandate from its inputs. By treating the mode as a participating vote, the gate safely preserves ambiguity. It holds the unknown open rather than forcing a false positive. To grasp the mechanical power of this gate, we have to unlearn our numerical instincts. The values 0, 1, and bottom do not exist on a quantitative integer scale. This diagram illustrates the information order. Here, hierarchy is strictly based on certainty rather than quantity. The unknown bottom state sits at the root, while 0 and 1 sit above it on an equal, defined tier. Moving vertically from the bottom root up to a 0 or a 1 represents a literal, measurable gain in information. Moving horizontally between 0 and 1 does not increase knowledge. It simply replaces one certainty with a contradictory certainty. This specific structural order allows the Trigate to satisfy a critical mathematical law known as monotonicity. A monotone function dictates that if any single input gains information, moving upward from the bottom state, the gate's final output can never lose information. An existing defined majority cannot be dismantled simply by clarifying an unknown input. In this mathematical architecture, understanding more can never make the system understand less. This property scales. We can move past the microscopic view of an isolated gate and compose massive networks of interconnected trigates. Because each individual gate is mathematically monotone, the entire interconnected network functions as a unified monotone interpretation operator. This complex topological network initializes in a state of maximum ambiguity. Every node is uniformly gray, trapped entirely in the unknown bottom state. We begin by injecting defined external information, zeros and ones, into the outer edges of the grid. As these signals cascade inward, nodes with clear majorities flip to solid colors. Nodes with conflicting inputs safely remain gray. The system crystallizes piecemeal. Highly defined areas stabilize immediately, while ambiguous areas remain open without causing the rest of the network to crash. Eventually, the cascade slows and halts. Applying the interpretation operator yields no further structural changes to the grid. In mathematics, this frozen state is called a fixed point. Reaching a fixed point signifies the system has achieved internal coherence, having stabilized all possible majorities from the available input. But achieving a mathematically coherent fixed point is not synonymous with finding the truth. A completely false interpretation can remain perfectly stable within isolated, artificially controlled boundaries. The illusion holds right up until it makes contact with reality. The ultimate test of a logic system is whether its internal coherence can survive the continuous injection of new, contradictory information from an expanding environment. Understanding, as modeled by the Trigate, is not the imposition of an answer onto an unknown. It is the stabilization of information into a structure that holds firm even as the dataset expands.